All right, section 9.4 of this insurance and probability unit. This is compound probability. So we're going to be looking at independent events and dependent events and trying to differentiate between them. Let's start with this scenario here about this game that is being played. I'm going to play a video for you, give you a little bit of it, and then you can consider the situation, decide what you would do, and then we'll look at the math behind it. Let's get this going.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be?
All right, answer the question. Would you rather be player 1 when you win with a 1, 2, 3, or 4, or player 2 winning with a 5 or a 6? So write down your answer number 1 on page 21 and then give a reason. And come back here to see how it goes. All right, everybody should have an answer. Let's see how this shakes out.
At first glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. There are 36 possible combinations, each with exactly the same chance of happening. Mathematicians call these equiprobable events. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win, and if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1, and 20 give player 2 the win. You could think about it this way, too. The only way player 1 can win is if both dice show a 1, 2, 3, or 4. A 5 or 6 would mean a win for player 2. The chance of one die showing 1, 2, 3, or 4 is 4 out of 6. The result of each die roll is independent from the other, and you can calculate the joint probability of independent events by multiplying their probabilities.
And we've seen that before. When 2 events have to happen together, multiply their probabilities together. So 4 out of 6 times 4 out of 6 would get the job done here.
The chance of getting a 1, 2, 3, or 4 on both dice is 4 out of 6 times 4 out of 6, or 16 out of 36. Because someone has to win, the chance of player 2 winning is 36 out of 36 minus 16 out of 36.
There's your complementary probability, right? You could take 1 minus the previous answer to get the new one.
20 out of 36. Those are the exact same probabilities we got by making our table. But this doesn't mean that player 2 will win, or even that if you played 36 games as player 2, you'd win 20 of them. That's why events like dice rolling are called random. Even though you can calculate the theoretical probability of each outcome, you might not get the expected results if you examine just a few events. But if you repeat those random events many, many, many times, the frequency of a specific outcome, like a player 2 win, will approach its theoretical probability. That value we got by writing down all the possibilities and counting up the ones for each outcome. So, if you sat on that desert island playing dice forever, player 2 would eventually win 56% of the games, and player 1 would win 44%. But by then, of course, the banana would be long gone.
All right, so let's go back and explain about why this works this way. So we're talking about compound probability here, right? So player 2 ends up having the higher probability. Player 2 comes out ahead. And the way it was explained is that there are 16 ways for player 1 to win. And that can be done by doing 4/6 times 4/6, which is 16 over 36. So 16 ways for player 1 to win. And then if you do all 36 or just one whole minus the 16/36, that's going to give you 20 out of 36. So player 2, this is all player 2's calculation. Player 2 is going to come out ahead by 4 wins. So what surprised you about the result? Well, that's up to you to decide. If you picked player 1 and player 2 comes out better, then maybe there was something that surprised you about it. So just put something there that was a surprising result for this situation. All right, let's go over to page 22 and look there. So we are dealing with some definitions here, independent and dependent events. We know how to talk about sets and subsets using mathematical language. Let's look at multiple events. So here's a situation where a basket contains numbered balls from 1 to 32, kind of like a lottery. You're going to choose 2. If you choose 2 even balls in a row, you win. Now there are 2 events in this situation. You're going to pull the first ball, that's the first event, and then you're going to pull the second ball, and that's the second event. An important question when considering this is, are these events independent or dependent? So independent means the one does not affect the other, right? So they're just completely separate from each other. And dependent would be if the first event actually has an effect on the second one. All right. So in this example, you flip a coin twice. First flip is at 1/2 probability to get heads. And then if you flip the coin again, the coin doesn't know that you already flipped it once. It's not affected by the first flip, and so that's still a 1/2 probability, and it always will be. All right, so give an example of 2 independent events. So you could roll 2 dice. If the first die comes up a 2, that does not change the odds of the second die coming up 1 through 6. So the roll 2 dice would be an example. In a situation out in the world, whether it's raining is the first event. And let's say what TV show you watched yesterday. Okay, so the weather outside has no idea what's on your Netflix account, right? These are completely different from each other. So totally independent events from each other. The third one could be, say, event 1 is what you ate for breakfast. And something unrelated to that could be something like someone, let's do it this way, what somebody in Europe ate for breakfast. Right, so what you eat here has nothing to do with what those people across the ocean are eating. Okay, so these are independent events, things that do not have anything to do with each other. Dependent events are where the outcome of the first changes the second one. So you're going to choose 2 students from a classroom of 20 to win a free homework pass. That's the scenario. There are 12 boys and 8 girls in the class. If you select a girl, the classroom has now changed, and that's the key. This has to do with whether we replace the first selection. And we are not, because we've chosen somebody, right? So now there's only 19 students left and only 7 girls. So the whole sample space has changed. But if you chose a boy first, we'd still be down to 19, but we'd have all 8 girls. So the second event probability depends upon the outcome of the first one, right? So an example of that would be, let's say, whether you wear a coat. And if it's snowing. All right, so those events are related to each other. It's not a perfect thing, you know, it's not like every time it snows somebody wears a coat, and it's not like every time somebody wears a coat it's snowing, but if it is snowing, you are more likely to wear a coat, so that's going to change that probability. So one somewhat depends upon the other. All right, and another one could be what seats two people choose in a classroom. So picture two good friends walking into class the first day of school. Wherever the first one sits is going to affect where the second one sits. There's only two O's in the classroom. Okay, so this is a scenario where the first event can definitely change the second event. They're not completely independent of each other. So there are, a lot more examples in each category that you could come up with. So returning to the original example, a basket contains numbered balls from 1 to 32. You're going to choose 2 in a row. You choose a ball. Record the result and do not replace the chosen ball. What happens to the sample space then? That basket. What happens to the basket when you don't replace the ball? Right, that ball is now outside the basket, so there's only 31 remaining in the basket. That is going to change the denominator. It's going to change the probability. So these two events are considered to be dependent because I didn't replace the ball. And so the sample space changed. So if I was doing a probability problem with this, the first fraction would have a 32 in the denominator. The second fraction would have a 31 in the denominator because I didn't put the ball back. Okay, if you did replace the ball before selecting the second ball, would they be independent or dependent? Well, if I take a ball out, do whatever I'm going to do with it, and then put it back in, well, then the basket now contains all 32 balls again. So now it's independent because the second drawing has nothing to do with the first drawing. It's just the same sample space all over again. So independent, same sample space for second event. Second event. Okay, so replacing the ball is the key there. If you have replacement, then that means you're resetting it and the second event is not affected by the first one. If you don't replace it, then it is dependent because the first event changes the second one. Okay, so you're going to go into Google Classroom and open up the card sort that's there. You are going to want to put the headers in the corners away from everything else, and then you're just going to drag the cards onto those headers so that it gives you a whole stack of cards. It does get a little bit weird when it tells you how many are right. It'll tell you if it's totally right, but if you have even one wrong, it's not going to tell you have one wrong. It's going to tell you have like half of them wrong. So don't worry about anything with the updated score until it's perfect. And if it's not perfect, drag one off the stack and put a different one on. All right, so that's what you're doing next.